Hey guys, welcome back to another lecture video for Chem 115. In this video, we are going to continue our discussion of titration curves. More specifically, we are going to learn how to sketch the titration curve of a solution in which our analyte is our strong base and the titrant is our strong acid. And so comparing these calculations to the calculations that I did in the previous video, you'll be able to see some similarities and some differences. And so let's go ahead and begin. In this scenario, we have a 100 milliliter sample of 0.100 molar potassium hydroxide, and it's titrated with 1 molar of hydroiodic acid. Now, the main goal is for us to determine the pH of the solution as we add titrant to the analyte. And then from the results of each part of each calculation, we're going to go ahead and sketch a titration curve. So the first thing that we need to do is identify which of these two substances is our analyte or titrant. And so once again, we're going to use clues within the sentence to determine which is our analyte or titrant. Since the 100 milliliter sample is referring to the potassium hydroxide, you can imagine that potassium hydroxide is inside the Erlenmeyer flask because that's our sample. That's what we are analyzing. And so therefore, potassium hydroxide will be our analyte. Okay, we're analyzing the sample, and the sample happens to be potassium hydroxide. And so this analyte is going to go into the Erlenmeyer flask. Now, hydroiodic acid, that's the other substance, that's the other component, and this is going to be our titrant. And it's going to be found in the burette. And what we're going to do is we're going to summarize everything that I've written here in this first sentence of this paragraph into an image. And so our goal is to determine the pH of the solution. When we have a 1.00 molar hydroiodic acid in our burette, and inside our Erlenmeyer flask, we have a 100 milliliter sample, and the concentration is going to be 0.100 molar. Okay. And so we're going to go ahead and use this image as we work through each part of the problem, just to help us keep everything organized. All right. And so looking through each part, the first thing that we're going to do is we're going to calculate the initial pH of the analyte, and then we're going to calculate the pH when we add 9 mils. Then we're going to calculate the pH when we've reached our equivalence point. We're going to calculate the pH when we add 15 mils. And then last but not least, we're going to sketch the titration curve. So let's go ahead and perform the first task. So we're going to calculate the initial pH of the analyte. And so since we're trying to determine the initial pH of the analyte, we know that we're not going to add any titrant. And so therefore, the volume of the titrant, now if you look at the identity of the substance, this is the acid, and this is the base. And so therefore, I'm going to go ahead and abbreviate volume of the acid to represent the titrant in this scenario. In the previous video, it was VB, which is the volume of the base, and that was our titrant in the previous example. So VA is going to be 0.00 milliliters. And so if we're just trying to calculate the initial pH, that means we're going to think about how potassium hydroxide is going to interact in water. So here we have potassium hydroxide, and when we place that in water, what we get is simply potassium ion and hydroxide ion. And so if we want to calculate the pH, what we need is the equilibrium concentration of H plus or the equilibrium concentration of OH. And so if you know the equilibrium concentration of either of these two, then we can go ahead and determine the pH through some of these equations that we've kind of been going over this whole chapter. And so I see hydroxide present here at the as my product. And so I'm going to go ahead and describe the course of the chemical reaction, this dissociation, through the ICE table. So I'm going to go ahead and write initial, change, and equilibrium concentration. And so since there is no reaction that's occurring, there's no acid-base reaction that's occurring, I can just go ahead and keep everything in terms of concentration, right? I'm not really adding anything into this Erlenmeyer flask. I'm just simply asking if I have this amount in this Erlenmeyer flask, what would my pH be? Okay. And so my initial concentration is going to be 0.100 molar. And my change is going to be minus 0.100 molar. Why is that? Why is it not minus X? The reason why it's not minus X is because potassium hydroxide is a strong base. And we know that strong bases, strong acids, they ionize 100%. So at equilibrium, we have nothing remaining of potassium hydroxide. All of potassium hydroxide has been converted into potassium ion and hydroxide ion. And so just to complete this ICE table, so here we have two products, potassium and hydroxide. Remember that we're trying to calculate the pH. And so the potassium is not really going to assist me in that endeavor. In addition, the potassium does not affect the pH of the solution based on one of the previous lectures that that I already went over. All right, so that tells me that if I have an equilibrium concentration of hydroxide of 0.100 molar, then I can go ahead and take the pOH of this value by taking the negative log of it. And so if you take the negative log of 0.1, you're going to get 1.000. So that's my pOH. Now, I'm not trying to figure out my POH, I'm trying to figure out pH. So I'm going to do, what I'm going to do is I'm going to say pH is equal to 14 minus my POH. Okay, I'm going to plug that value in, and therefore my pH is equal to 13.000. And so after I did a quick ice table and I applied the definition of POH and pH, I was able to determine that the pH of the solution is 13.000. And this is when the volume of the titrant, in this case the acid, is equal to 0.00 milliliters. Right? We didn't add any titrant whatsoever. We allowed this potassium hydroxide to do its thing, to separate, and then we took a pH meter, stuck the pH meter in, and the pH meter told us that the pH is 13. I mean, technically that's not what we did here. We performed the calculations, but this is the calculation that one could expect the computer to do if we had a pH meter on hand. Anyways, cool. So we figured out the first part. We calculated the initial pH of the analyte. And so the next thing that we're going to do is we're going to calculate the pH of the analyte after 9 mils of titrant is added. And so I'm going to go ahead and just copy one more item here. So I personally like to have pictures. It'll just help me understand what's happening in this problem. You guys don't necessarily have to draw pictures if it doesn't assist you. All right, so now that we calculated the initial pH, what we're going to do is we're going to still calculate the pH. However, this is after we added 9 mils of titrant. So here we're adding 9.00 mils of hydroiodic acid. All right, and so if we're adding this acid to this base, okay, we do get an acid-base reaction. Okay, and so here we have hydroiodic acid reacting with potassium hydroxide, and that's going to produce, actually the arrow's one way, and so that's going to produce water and potassium iodide. So everything here is aqueous because everything is inside a solution. And so since a chemical reaction is occurring, what we want to do is we want to figure out the pH, the equilibrium concentration after the reaction has occurred. And so this will invite us to use our ice table once again. And so before I write my ice table, I'm going to write a net ionic equation such that all of my spectator ions are gone. So this is going to be simply H plus, my hydroxide, and since I produce water, this would be my reaction. Okay. All right, so in other words, potassium iodide are spectator ions, so I don't really need to include them in my equation. And so since we added this H+, so this was our titrant, to this hydroxide, which is our analyte, we know that some amount of the titrant is going to react, we know that the titrant is going to react with the analyte. And we want to know how much remains after the reaction occurred. So we can go ahead and set up an ice table to quantify this change. Now remember, since a reaction is occurring, I'm going to go ahead and use moles to determine how the amount is changing through the course of the reaction. Okay. Now, if you wanted to use molarity, feel free to do so, but make sure you guys recalculate the concentration when 9 mils was added to your Erlenmeyer flask. And so to figure out the moles, I'm going to go ahead and just multiply these two, molarity and volume. My volume has to be in liters because molarity is in liters. And so I'm going to move the decimal place 3 times to the left, 0.00900 liters times this by 1 mole, 1.00 mole for every 1 liter. Okay, so that's what I'm grabbing, that 1 mole from what I just underlined. And so if I multiply that, that's just the same number. So it's just going to be 9.00 times 10 to the negative 3 moles of HI, which can also be written as just H+. Okay? Since iodide is an anion of a strong acid, it doesn't affect the pH of the solution. So for the base, I'm going to do the same thing. I'm going to figure out the number of moles. And so I'm going to move the decimal place 3 times to the left to convert milliliters to liters. So 0.100 liters times this by 0.100 moles over 1 liter. Okay. So I'm grabbing that 0.100 from that value. And if I multiply these two values, I'm going to get 1.00 times 10 to the negative 2. And this is the number of moles of my base that I have. And the active part of the base is hydroxide. So now that we have the number of moles of acid and base, I'm going to go ahead and put that in my ice table. All right, so here in this case, in this example, we have these two substances. We have the initial amounts. So once again, think about these acids going to war with a base. They're going to cancel each other out once one of them hits each other, et cetera, et cetera. And if you look at the value, the one that has the least will be completely consumed. And so since 9.0 times 10 to the negative 3 is the lesser amount between the two initial values, I'm going to go ahead and subtract them. All right, and so this is going to be nothing. Well, I apologize. It's not nothing. It is, we do produce 9.00 times 10 to the negative 3 moles, but we're not really going to consider it in terms of our calculations because water in liquid state is typically ignored in the mass action expression. But I'll just leave it there for now. So at equilibrium, it looks like we do not have any more acid. Okay, so remember, acid was our titrant. So the amount of the amount of titrant that we added into the Erlenmeyer flask was completely neutralized by equal amounts of the hydroxide. And so if 9.00 times 10 to the negative 3 moles of the hydroxide was consumed in the process, then we're simply going to subtract these two values to get us the equilibrium amount in terms of moles. And so that value is going to be 1.00 times 10 to the negative 3 moles. And this is how much hydroxide remains. Okay. All right. And so since we have, it looks like we don't have the equilibrium concentration of hydrogen ions. What we do have is the equilibrium concentration of hydroxide ions. And so either one of these will give us the pH. And so if I have the equilibrium concentration of my hydroxide, then I can probably figure out the pOH by taking the negative log of it, and then I can subtract it from 14, or 14 minus pOH is going to give us the pH. Okay, and so it's okay that you don't have any hydrogen ions remaining, and we only have the hydroxide. We can figure out the pH just from using that value. But what I want to remind you guys is that for me to calculate the pOH, everything has to be in molarity. And so right now we just have moles. And so what we're going to do is we're going to convert moles into molarity by taking the result, 1.00 times 10 to the negative 3 moles of the hydroxide. And we're going to divide it by the total volume. And so the total volume is the initial volume plus the amount that we added to it. And so 100 plus 9 is 109 mils. And so the total volume is 109 milliliters. But since we're trying to calculate molarity, we know that molarity is in moles per liter. And so therefore, we need to move that decimal place. We need to convert milliliters to liters. And I'm going to move that decimal place 3 times to the left to express it in terms of liters. And so if I plug in this value in my calculator, what I'm going to get is 9.1 7 times 10 to the negative 3 molar concentration. By now you guys should know the definition of pOH, and so I'm just going to go ahead and take the negative log of that number, and I am going to get 2.037. Oops, what did I write for? 037. Okay. So notice I have 3 sig figs, 3 places after the decimal. So to calculate my pH, which is what I'm really trying to solve for, I'm going to take 14 and subtract it from the value. I'm going to subtract it with pOH. And so it's going to be 11.963. So hopefully by now, after watching several or many of these lecture videos, you guys know how to calculate the pH from concentration of hydroxide. And so this is going to be the pH when the volume of the acid, remember this is the titrant, is 9.00 milliliters. Okay. And we're done. So going back to our questions, did we calculate the pH of the analyte after 9 milliliters of titrant was added? Yes. We found that that was 11.963. All right, so let's go ahead and do part C. So for part C, we're still going to calculate the pH of the analyte when the equivalence point is reached. And so I'm going to go ahead and just copy one more item. That one's too messy. I'll go ahead and just copy the original. Okay. So once again, when you've reached the equivalence point, that means that the number of moles of strong acid is equal to the moles of strong base. Oops. So that's a specific property of when you associate the word or the term equivalence point in a titration. Equal number of moles of strong acid and equal number of moles of strong base. And so it doesn't matter what you calculate, the moles are equal to each other. And so therefore they neutralize each other out. Right, so just like think of video games or whatnot. If one thing is canceling out the other, then you have nothing left. And so it's neutralized. And so what is the pH when everything is neutralized? So if you said 7, then you're correct. And so here in this case, the pH is equal to 7 at the endpoint. Now this problem didn't tell us how much titrant. So how much titrant do we need for us to reach an endpoint or equivalence point such that the pH is equal to 7.000? And so to figure that out, we need to use our modified dilution equation. Okay. So MA times VA over NA equals to MB, VB, NB. And so which variable are we going to solve for in this equation? Okay. And so we want to figure out the titrant, so that we need to figure out the volume of the titrant of the acid that we're putting in. And so we need to solve for VA. So let's plug what's given. I have a 1.00 molar concentration. My molarity for my base is going to be 0.100 molar. The volume of my base is going to be 100.0 milliliters. So let's talk about Na and Nb. So that's going to come from the coefficient of this acid-base neutralization reaction. So notice that it's a potassium hydroxide that's reacting with hydroiodic acid. And so the result that we get is going to be water and the salt, which in this case is potassium iodide. Now, if you check this equation, the chemical equation from left to right, you'll see that this is a 1 to 1 to 1 to 1 ratio. So this is going to represent NB, this is going to represent NA. So we're going to put 1, and we're going to put 1. And so if we clean up our work, we just get 1.00 molar Va over 1.100 molar times that by 100 mils over 1. Okay. And so if you calculate all of this, this is just going to be 10 mils. And so when we add 10 mils of titrant, then that's going to give us the equivalence point. So this will be the end point of our titration. So this is where that phenolphthalein, if you will, right? It's not exactly phenolphthalein, because the equivalent or the end point for phenolphthalein is more basic than neutral. So if you guys can imagine that change in color from colorless to pink or whatever to indicate the end point, you can kind of associate that experience into this question, right? However, it's I have to repeat and I have to emphasize the end point of the phenolphthalein is not 7. It's basic. It's more basic than that. Okay. And so when the pH is equal to 7.00, then the volume of the acid is just going to be 10 milliliters. All right, so let's look at our list. We solve part C. So the last thing that we need to do is solve part D. Okay. And once we have these 4 points, after we solve for part D, then we're going to go ahead and use the result from A through D to sketch our titration curve. And then one last thing that I need to add is my picture. And so I'll probably just erase some stuff here. Just to kind of reset this image for this problem. All right, let's go ahead and start. So we're going to calculate the pH once again of the analyte. So we're always trying to calculate the pH when 15 mils of titrant is added. And so if the end point occurred when 10.0 mils of our hydroiodic acid was added, then that means if we add an extra 5 mils for a total of 15 mils, then we'll have excess titrant. So the end point is 10 mils of hydroiodic acid at, so not at, when 15 mils is added from the initial from the initial point, let's just say, we're going to have an abundance of titrant. And so this is where we're going to see that huge shift in our titration curve, right? So if you recall from the previous two lectures, we always have that vertical curve, that very, very steep slope. It's almost vertical. And then all of a sudden, it flips over to the top side or the bottom side, depending on how you're looking at the titration curve. But that's going to represent the abundance of the titrant that remains inside the solution because there is no more of the acidic or the basic analyte that's in the solution. All right, so that was just a side note. So let's just go ahead and do the calculation. And so if you don't recall this little side note, then that's okay. All you guys need to be concerned about is be able to do the calculation. And so since we're adding acid to base, this is another acid-base neutralization reaction. So that we need to write a chemical equation to reflect the reaction that's occurring in solution. Okay. And so this is very similar to the chemical reaction that we wrote in part B of this problem. And so very similar to what we did in part B of the problem, we're going to go ahead and write the net ionic equation. And so in this case, I'm just going to write H plus and OH minus because iodide and potassium are spectator ions. And I'm going to drop this completely so that way I just have liquid water remaining. Okay. And so whenever I have an acid reacting to my base, I have a reaction. And whenever I want to describe the progress of the reaction, if I want to quantify it, I personally want to do everything in terms of moles. Now, if you want to do molarity, then feel free to do so. Just make sure that you're recalculating the concentrations. And so I'm going to do ICE. And so what is my initial moles of acid, and how much of my acid is going to react with moles of base? Okay. And so once again, I can determine that by multiplying the molarity and the volume. And so if we do that calculation, I have 0.100 liters. So I converted my volume into liters. And then I'm going to multiply that by my concentration, 0.100 moles of hydroxide over 1 liter. That cancels, leaving me with 1.00 times 10 to the negative 2 moles of hydroxide. And so I'm going to go ahead and place that over here, 1.00 times 10 to the negative 2 moles of the hydroxide. Next, we're going to go ahead and figure out the number of moles of hydrogen ions. And to do that, we're going to take this molarity and multiply it by the volume. And I need to express that in liters. So 1 times anything is itself. So you just need to express the milliliters into liters. And so what I have is going to be 0.0150. How many zeros do I have? 2 zeros. So this is the number of moles. Now, if I express it so that the magnitude are the same, I'm going to do 1, 2. And so I'm going to get 1.5 times 10 to the negative 2. Moles. And so I'm now going to look at the magnitude. The magnitudes are the same, so I'm just going to compare the value. And so 1.50 is greater than 1.00. And I want you guys to recall that the H plus was our titrant, and our hydroxide was our analyte. And so after you pass the equivalence point or the end point, that means you've completely consumed the component that's inside the analyte. So you've completely consumed all of the hydroxide. And anything past the end point or the equivalence point will represent the excess of the titrant. And since our titrant is an acid, it makes sense to have the resulting pH to be very low compared to the initial pH. And so I'm going to go ahead and subtract 1.00 times 10 to the negative 2 moles. 1.00 times 10 to the negative 2 moles. And this will cancel out, leaving me with just 0.500, 0.50 times 10 to the negative 2 moles. Okay. All right, so 1.5 minus 1, that's 0.5. And so this is the number of moles of hydrogen ion that I get. Now, and this is the number of moles I have at equilibrium. So this is cool because now I can go ahead and determine the pH. But before I do so, I need to make sure that I convert all of my amount in terms of molarity. And so I'm going to take that 0.50 times 10 to the negative 2 moles. And I'm going to go ahead and divide it by the total volume. So let's go ahead and look at what's happening. We have 15 mils, and we're adding it to 100 mils. And so overall, the total volume is going to be 115 milliliters. And so if I want to express that in liters, which I should, because molarity is moles per liter, I'm going to get 0.115 liters. And so at this point, I'm just going to go ahead and type into my calculator 0.5 times 10 to the negative 2. Divide this by 0.115. That's going to give me a concentration of 4.347. 8, whole bunch of numbers, times 10 to the negative 2. All right, and so here we'll just go ahead and make sure to follow our sig figs according to our math. So this is 2 sig figs. Okay. So we're just going to record up to here. So let's just go ahead and take the pH of this. So the negative log of the answer, it's going to be 1.36. And this is going to be the pH when we add 15.00 milliliters of our acid, okay, our titrant. All right, so we now completed part D. We calculated the pH of the analyte when 15 milliliters of titrant is added. So the last thing that I need to do is summarize all of my answers and then plot them on a graph. And so I just want to make sure that I have enough space here. So I have, what's happening? I have 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And so when you guys are sketching your titration curve, please remember that the pH is on the y-axis. And I'm just, the the scale is always from 0 to 14. I mean, it can go higher, it can go lower, but based on our calculations, it actually doesn't go higher than 14 or lower than 0. And if you look at the range and volume, our volume was like from 0 to 15. So 15 was like the maximum volume, right? That was the last volume that we calculated. So the x-axis is representing the volume of titrant added. And this is VA in this scenario. And so I can probably just do this by ones. I want to expand, make sure I have enough. I'm going to make sure I'm going to utilize my graph to the max so I can get more of a stronger feature of the graph rather than everything being squished. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so this is my volume that I've added on the x-axis. All right, so let's go ahead and summarize the values for all 4 points. From part A, when the volume of the acid is equal to 0.000, the, or 2 zeros is fine, the pH was, it should be 13, right? So it's 13.000. For part B, when we added 9 mils, the resulting pH was 11.96, if I recall. Part B, 11.963. Part C, when the volume of my acid was 10 mils, when I add 10 mils of my titrant, which is my acid, the pH is going to equal to 7.000. Okay. And last but not least, the fourth point is what you see on the screen, top left corner. So when my VA is 15.00 mils, when I add 15 mils into my Erlenmeyer flask, the pH of that solution is going to be 1.36. Okay. All right, so we're going to plot these 4 points, 0 and 13. So here's 0 and there's 13. Boom, that is the first point. Okay. So next point is 9 and 11.963. That's very close to 12. And so 9 mils is going to be right here. So please use a ruler. Here in this case, I can just go ahead and approximate. And 9 mils. So it's right about here. Okay, erase that. Oh no, 12. Oops. Okay. It's just underneath 12. Okay. So that is point B, and then C, 10 mils and 7. Oops. So here's 10 mils. Just draw it straight as possible. Oops. whatever. So 10 mils, pH of 7. Okay, so it's this point. And then last but not least, I have 15 mils, 1.36. So here's 15 mils. Oops. And 1.36 is slightly above 1. So this is C, this is D. All right, and so we know that C is going to represent our endpoint or our equivalence point. And so this is really where our graph is going to slope very steeply, okay? And so what you're going to do is you're just going to connect the points, and as you approach point C, you want to start curving your titration curve. Once again, there's probably many different ways for you to do this precisely, but right now we're just sketching our titration curve, so we're just going to do a rough sketch. Okay, and we probably do need more points for us to get a more precise graph. But so for example, if we had 2 points at the very bottom instead of 1 point, we can go ahead and use like the slope. So for example, I can go ahead and connect these 2 points. So that's a slope going downwards. And let's just say for example, I had like a point here. Okay, I can go ahead and put that point or put a line through those 2 points to get a straight line, and then I can go ahead and put a line right through, okay, something like that. Just kind of give me an idea of how to draw my titration curve. All right, so that point never existed, by the way. I'm just making it up. All right, so this is pretty much it for for part E. So for part E, we were able to sketch our titration curve using the results from part A through part D. And so I want you guys to compare and contrast the titration curve from this video and the previous video. So hopefully hopefully you guys were just taking notes along the way or screenshotting specific aspects of the video. But if you guys notice the difference between strong acid, strong base, or strong base, strong acid titration curve is the initial and how the graph kind of looks. And so we'll go ahead and compare and contrast the titration curves for 4 titration curves in a later video. But I just want to throw that out there. Think about the similarities and differences between them. All right, that's pretty much it. In the next video, we'll talk about strong base, weak acid titration curves. Should be fun. See you later. Bye.